Assalamualaikum warahmatullahi wabarakatuh. Hello, my name is Muhammad Ardien. For this time, I'm gonna present to you about a topic that I have been interested in mechanical fluids, which is a profile flow on an object. So basically, in mechanical fluids, there is so-called like profile flow on an object at a point where the flow or the characteristic of the flow is different at a point from that point to another point. So let's get into the details. So this is the frame. What's how am I gonna explain it? This is the I5 process, which is intention, initial thinking, idealization, and instructions. So in my intentions here, I hereby made this presentation to evaluate myself about mechanical fluids to understand more about its fundamentals and as a believer of God. My initial thinking about this is definitely to start off the process of learning mechanical fluids, we have to define mechanical fluids in definition. So yeah, after that we get to the idealization, which is I'm gonna be mentioning about the type of profile flow in mechanical fluids, and the instructions. I'm gonna explain an application of the profile flow in mechanical fluids. So let's get started, shall we? So what is mechanical fluids? Fluid mechanics is a study of fluids at rest and in motion. Usually, when we refer to a fluid that is at rest, no motion, we call it we call it fluid statics. So it basically revolves around the momentum, the force, the weight on the fluid that is happening on like a glass, like for example this bottle right here. So this fluid will create a weight down at the bottom of the bottle, which create pressure at the bottom. Usually, the bottom has the highest pressure. Actually, not pressure, the weight, the force. The force and the pressure is deep at the bottom, at the lowest point. That is when the pressure is the biggest. So yeah, so that's fluid statics. And there's also fluid kinematics and dynamics. So usually fluid kinematics and dynamics we refer to like a fluid in motion. So we refer to the continuity equation, Bernoulli equation, and other type of um, fluid fluid and energetic section. So basically, this refers to the work, to the acceleration, to the velocity, all that kind of stuff that are a fundamental in a moving object. So a fluid is defined as a material that continuously deforms under a constant load. So fluid, it depends on the where the fluid is from, like a fluid flowing from a pipe. The water flowing from a pipe, we can call it continuous deformation. So the fluid continuously deforms until it flows in one point to another point. There are five relationships that are most useful in fluid mechanics problems. There are kinematics, stress, conservation, regulating, and constitutive. Now let's get to the topic that I want to discuss about this time. So the profile flow, we can break it down into three types. That the first one is viscous flow, and then two is open channel flow, and three is compressible flow. So I'm gonna explain about viscous flow first. So viscous flow in fluid mechanics refers to the type of flow where the fluid's viscosity or internal resistance to flow plays a significant role. The study of viscous flow is essential for understanding how fluids behave in real-world scenarios, where ideal fluid assumptions do not hold. So basically, This is like type of flow that are in some point at a point which is different when when the fluid is at another point. Like, for example, the type of flow that flows, the type of the characteristics of the fluid that flows at, for example, this point, and at this point will be different. It's all based on the, well, it's based on the velocity and then the disturbance of the fluid and how it flows on the viscous flow section. In most cases, viscous flow plays a part in analyzing the flow profile on a pipe flow. The flow profile can be divided into three types that are laminar flow, transitional flow, and turbulent flow. So, turbulent flow. Let's start with the smoothest one, which is laminar flow. As you can see, the flow on a pipe is so smooth that it considers to be so ideal. But translational, there's a bit of bumps right here and there. It's not too tight. It's not that really tidy. The flow is not that tidy, but it's close to tidy. Like in the middle of very distorted and very steady. But in turbulent, it's very distorted. Like the flow is so like not that tidy. There's like a lot of bumps right here, which is why this type of flow is not very is not what you call it. This part is so like very, usually this part is where like the energy is like very big, like the work from the fluid is very big, like there's a lot of movement here and there, and the directions are not one direction. There are a lot of direction, like how do I say this? So the direction of laminar flow usually just one point to another, like maybe just this right to left, right this is laminar flow. As you can see, how my cursor is moving. This is laminar flow. This is transitional flow. So like this, how my cursor is moving, like it's not moving in a straight line. It's kind of like there's like a wave kind of movement, and then at the turbulent there's like, it's the movement is like this, like it's all over the place. So that's how we can define the fluid on a pipe flow, on what type it is at the point, based on how the fluid is moving. Okay, we usually determine the profile of the fluid using Reynolds number equation. We can di- we can we can tell on how what type of flow is flowing at a point using Reynolds equation, which is Reynolds number equals density of the fluid times the flow speed times the characteristic linear dimension divided by the dynamic viscosity of the fluid. So there's with Reynolds number you can determine the flow happening at a point of pipe. As in this picture right here, it tells us that usually the Reynolds number that are lower than 2300. Reynolds is a dimensionless unit, so there is no like units behind Reynolds number. Just so when it's at below 2300 Reynolds, it's called a laminar flow. The laminar flow has a characteristic of predictable and slow mixing. But when it's at the point when it reaches more than 2300 in Reynolds number, with and until under a bit of 4000, it's called transitional. So basically, this is like the middle of the laminar flow and the turbulent flow combined, like 50-50. So at this part, the turbulent outbursts. When the Reynolds number is at 4000, it's the movement is unpredictable, and it's also in a type of rapid mixing. Yeah. So we can define the flow of the flow of the fluid at a point in a pipe flow using Reynolds equation. So let me give an example of how we can of like a type of question. So this question is, we are given water at temperature of 550 Fahrenheit flows through a pipe of a diameter of 0.73 in and into a glass shown in this. Like the flow is flowing like this. We need to determine the maximum time required to fill a 12 ounce glass. So the volume is equals to 0.0125 feet cubics with water if the flow in the pipe is to be laminar. So yeah, we assume at A the flow is laminar. We can repeat this calculation if the water is 140 Fahrenheit. Okay. B, the maximum time to fill the glass if the flow is turbulence. Repeat the calculation if the water is 140 Fahrenheit. So basically, now A, we assume the flow is laminar. B, we assume the flow is turbulent. Okay, let's start from A, the solution. If the flow in the pipe is to remain laminar, the minimum time to fill a glass will occur if the Reynolds number is maximum allowed for laminar flow. Typically, Reynolds number equals to 2100. So I already told you before, this Reynolds number needs to be below 2300, which 2100 is okay. For I got this question from the book, and I think they use a reference of the maximum of Reynolds number for laminar flow is 2100. It's fine. It's fine. Laminar flow, you can define it wherever you want. It's between the 2100 and 2300 range, but 2100 is okay. So the max is 2100. Thus, V equals, so we using the Reynolds equation to so V is gonna be replaced here, and then we move the Reynolds number here, just the 2100, and then and then we get the density is 1.74 slugs per feet per second, feet cubics, and the dynamic viscosity is 2.73 times 10 minus 5, yes, pounds times s per feet squared at 140 Fahrenheit. Thus, the maximum average velocity for laminar flow in the pipe is V equals to 2100, which is the maximum Reynolds number for laminar flow, times mu, which is dynamic viscosity, per rho, which is the density, and d. So my bad. It's equals to 2100 times 2.73 times 10 minus 5, pounds times s per feet squared divided by 1.94 slugs per feet cubics times 0.73 per 12 feet. We get the velocity is 0.486 feet per second. Similarly, we have if we do 140 degrees Fahrenheit, similarly for V is equals to 0.1766 feet per second at 140 Fahrenheit, with V strip equals volume of gas, and the equation is V equals to QT. Q is the flow of the mass, and t is the time. So we can like move q here to the v, so we can define the time required. So t equals v per q equals to v per per 4 times d squared times v equals to this, and then we get 8.85 seconds at 50 degrees Fahrenheit. If we can calculate this at 140 degrees, you get t equals to 24.44 seconds. That's laminar flow. Now let's move on to the turbulent flow. We can assume it's Reynolds equals to 4,000, which here Reynolds equals turbulent is 4,000 at the minimal. If we want to define the maximum, is gonna be infinity, so we just assume it's 4,000. That's the point where Reynolds number is at minimum. So yeah, 4,000. We can use the equation that and the steps we used before for laminar flow, but this time we're using 4,000 Reynolds number, and the V equals to 4,000 times mu per rho times d equals to 0.92 feet per second. So we can calculate this, and then we get t equals to 4.65 at 50 degrees Fahrenheit. Similarly, if we try to assume it's 140 degrees Fahrenheit, we get v equals to 0.335 feet per second, and time is 12.8 seconds at 140 degrees Fahrenheit. Now I'm gonna move on to the open channel flow. So we've discussed about viscous flow before. Now the difference is here the open channel flow usually happens in rivers, the type of flow where it's open, it's like very open. It's very usually it's like the river, the canal, like the what's yeah, like the river. I don't know what the English for God is, but God in our house. I don't know the English, but yeah, it's the same as the river. It's called an open channel flow. So open channel flow pertains to the flow of liquids in conduits with a free surface open to the atmosphere, such as rivers, canals, and drainage ditches. Oh yeah, it's called drainage. Okay, I get. I forgot. I forgot. This type of flow is primarily driven by the gravity rather than pressure. Similarly to pipe flow, open channel flow can be laminar or turbulent, but since this is like an open channel, open channel flow, and it's a large dimension and it influence on gravity very much. It's mostly turbulent, as you can see. So yeah, we can call this laminar flow, but at this part is very turbulent, and at this point it continues to be laminar. Yeah, but so many things happening at open channel flow. We can divide it to be turbulent. So if at this picture we can see the section. So this is like a uniform flow stands for UF. So at this part and at this part is where the flow is very uniform. At this part, the flow is rapidly varying. Like at the first point, the flow, the shape of the flow is like this. But when at this point, it drastically changes, which is why it's called RVF. And this at this part, it's also it changed like from the fluid is down here and then it goes up here. It rapidly varies, but at this point it's UF. But at this point, the fluid comes down again, which we can define it as rapidly varying. And at this point, the liquid is sort of varying, but not very much. At this part is this bump, and then it gets like very straight again into like almost uniform flow, and then at this part the flow comes down again, which varies a lot. We can call it RVF, and then at this part the flow continues to be like stable, which we can call uniform flow. Okay, so the flow depth and a surface profile can vary, leading to different flow classifications such as subcritical, supercritical, and critical flow. These are distinguished by the Froude number. So, at viscous flow, we can determine with Reynolds, but at the open channel flow, we usually use Froude's number because this defines the type of flow, open channel flow that it's happening at a point on open channel flow. So this is a dimensionless parameter indicating the ratio of inertial to gravitational force. So as you can see right here, there are three types of profile flows based on Froude numbers. Usually at this part, I'm explain in a bit, but let's see the equation first. So Froude number is equals to V per and GL GL yeah GL in the roots, or we can call it V per C. C is the wave, the wave. So if the fluid layer is stationary, I'm gonna explain this part first. If the fluid layer is stationary, the wave moves to the right with speed c relative to the fluid and as the stationary observer. If the fluid flowing to the left with velocity of v bigger than c, the wave which travels with the speed c relative to the fluid will travel to the right with a speed of c c times v. So yeah, the actually it's at this part. This is where like the Froude number is below 1. So if we look at the equation V per C, if C is bigger than V, it will not reach 1. It will be below 1, the Froude number. So we can define this as where the Froude number is lower than 1. We can define this as the Froude number which is equals to 1, which V and C is the same, which makes when divided together equals to 1. And at this part is where V is bigger than C, which the Froude number is bigger than 1. So yeah, so with a speed relative to C times C minus V relative to the fixed observer. If the fluid flows to the left with V minus C, the wave will remain stationary. But if V minus C, the wave will be washed to the left with speed V minus C. Okay, so I'm gonna explain a little bit about the characteristic of of this picture right here. The following characteristics are observed when a wave is produced on the surface of a moving stream, as happens when a rock is thrown into the river. So basically, there's a rock right here that makes the flow of the water, the fluid creates a bump. Like if there's a rock here, it will like the fluid in the top will like come up here, and the height basically usually depends on how high is the rock. So yeah, if the stream is not flowing, the wave spreads equally in all directions. If the stream is nearly stationary or moving in a tranquil manner, or V, which is V lower than C, the wave can move upstream. Upstream locations are said to be hydraulic communication with the downstream location. That is, an observer upstream of disturbance can tell that there has been a disturbance on the surface because that disturbance can propagate this upstream to the observer. Viscous effects, which have been neglected in this discussion, will eventually dam out such waves far upstream. Such flow conditions, which is V lower than C, or we can define it as a Froude number lower than 1, are termed subcritical. So, this is where at the point which the flow is subcritical. Okay, so on the other hand, if the stream is moving rapidly so that the flow is greater than the wave, which is V bigger than C, no upstream communication with downward location is possible. And disturbance on the surface downstream from the observer will wash farther down the stream. Such conditions, V bigger than C or the Froude number is bigger than 1, are termed supercritical. So this part right here is supercritical. But of our special case where V and C is the same and the Froude number equals to 1, the upstream propagating wave remains stationary and the flow is termed critical. So basically at this point the flow is so critical, like V equals C, the Froude number is equals to 1. So this is stationary. Okay, so I'm gonna share an application of open channel flows here. So basically, at a certain location along the Rock River shown in the figure right here, the velocity v of the flow is a function of the depth of y of the river indicated in the figure below. A reasonable approximation to these experimental results is v equals to 5 times y to 2.3, where v is in feet per second and y is in feet. Okay, so the question asks, for what range the water depth will surface on the river be able to travel upstream? Okay, so the solution is while the river travels to the left with speed of v, the surface wave travels upstream to the right with speed of c equals to g times y in a route relative to the water, not relative to the ground. Hence, relative to the stationary ground, the wave travels at the right with speed c minus v equals to g d times y in the root minus 5 times y to 2.3, which we can calculate. We can just input. So gravity in feet is 32.2 feet per second squared times y. We can calculate this, and then we get this result. For the wave travel upstream, we can the travel upstream which is v is smaller than c. So this point v is smaller than c. This is part where it travel upstream. So we can like move the v here equals, which makes it c times v bigger than 0, which is 32.2 y in a root of 1.2 is bigger than 5 times y in a 2.3, which we can substitute in which we can eliminate these numbers, which give us y is lower than 2.14 feet. So we get the range, which is this part right here. Okay, that's for open channel flow. Now I'm gonna explain about compressible flow. So this is my favorite part in profile flow in mechanical fluids. Compressible flow deals with behavior fluids whose density changes significantly in responses to pressure variations, typically occurring at high velocities or under large pressure differences. This is especially relevant for gases, as liquids are generally considered incompressible due to their low compressibility. So the fluid that plays a part in compressible flow are usually gases. because most gases are compressible. But if we want to define a fluid that is incompressible, it's kind of difficult. So usually compressible flow is for fluids that are it's where fluids that if the fluids like liquid, it's kind of difficult to be compressible flow. So we usually just use fluids that are like gases, which are easy to be compressible flow. So yeah, the example is like a rocket moving so fast that it creates like a shock wave, which we can define with compressible flow. Planes, rockets, cars moving, motorcycles moving, we can define it as compressible flow. So compressible flow deals with behavior of fluids whose density changes significantly in response to the pressure variations, typically occurring at high velocities or under large pressure differences. This is especially relevant for gases, as I told before, as liquids are generally considered incompressible due to their low compressibility. Compared, if we compare this to incompressible flow, compressible flow assumes the fluid's density changes throughout the flow. So in our lesson at incompressible flow, we usually like the fluid density never changes. So we at our lesson before in mechanical fluids, we usually deal with fluids that are water, that are like liquid. Those are incompressible flow. But in this part at the compressible flow, we will deal with gases, which the density varies at point. We can determine if the flow is compressible or not by a Mach number, which is a unitless quantity in fluid dynamics that tells you how compressed is the object. It can be mathematically defined with ma equals to v per c, which if we look at open channel flow, it's kind of similar, but c here is defined as the speed of sound, and v is defined as local flow velocity. A common benchmark for determining if the flow is compressible or not usually is when the Mach number is above 0.3 or is equals to 0.3. At this level of Mach number, the changes in density becomes more significant and it's considered a compressible flow. So there are categories for a compressible flow that can be defined based on its Mach number. So at this point, if it's lower than 0.3, it's considered a incompressible flow. So we don't. It's not part of the compressible flow. So we do not talk about this. So at this part is where the compressible flow started. So at 0.3 above, it's subsonic flow until at this point is transonic flow, and at this part is supersonic flow, and at this part is hypersonic flow. This part right here is the one that is so big, is called hypersonic flow. So this is like very very big towards at this point. The speed becomes so the speed flowing is the fluid flowing around the body becomes so fast, and the compression on the object is so great. um Actually something can travel at this speed, but it's very hard to travel at this speed because the body need to be resistant to pressure, which we can achieve using aerodynamic materials like rockets. They use materials that can like that is so resistant to pressure. So when they are traveling so fast, the pressure on the created by the object flowing, the object flowing didn't compress the object. So as an object accelerates from subsonic to supersonic in a gas, different types of wave occurs. To illustrate, first of all, when an object is at like a stationary where it's not moving at all, is like this. So we draw a circle and a circle and a circle and a point. So this is like how we draw like how we can like show how an object is stationary. So at this point we can come to this picture right here. Uh, this is from my quiz I've done with Mr. Dai at a class. I use it because it's very informative. I use it again, very informative to put here, which if I didn't put, it's a shame. So yeah, we can so with this part we can divide it at this part right here. So this part stationary is the circle is aligned together very tidy. When at Sonic the Mach number starts to rise, which is around zero, is which is more than zero and but below one. This is called Sonic. This is when like the where like the circles are like compressing to the right, starting to compress, and at this part where the Mach number equals to one, the circle at the center touches the the left side of the circle, and then this also touches the left side, which creates like a distorted type of circle. But when it reaches more than one, the circle becomes so distorted. It forms what we call a Mach angle. This occurs when the Mach number is bigger than one, which creates a shock wave because why did it create shock wave? Because it's so fast that it's above the speed of sound, which if an object if an object travels at a speed of sound or above, it creates a shock wave, which we can illustrate is like this, and the compressibility effects start to occur, forming a wave that's sort of like a cone, which at the point creates an angle called Mach angle. This is supersonic. So when this occurs, the locus of this wave trailing behind the point creates an angle known as Mach angle or Mach wave angle. It can be mathematically defined as sin alpha equals to c per v, or we can divide as a simple thing, which is 1 per Mach number. So the Mach number is what? So we just divide it in this part and then 1 per Mach number. Okay, so this is the example of application I did in the quiz about compressibility effects, so at mechanical fluids. So I assume here like a jet plane moving at a speed of 1,000 miles per hour, we can define it as 447.04 meters per second, creating a shock wave as it travels. Does the air flowing in the plane considered compressible flow, or if it does, how big is the Mach angle created by the waves traveling? So we can define it. We can define Mach number using ma is equals to v per c, which the speed of sound is 343 meters per second. So we just put the numbers here. 447 per 343 equals to 1.3032. This is the Mach number, which, because this is above 1 and this is above 0.3, it is considered a compressible flow. And it's considered to be the type of compressible flow which is a supersonic because it is above 1. So we get it. The flow is compressible, but how big is the Mach angle? We can divide with this. Sin alpha equals to 1 per ma, the Mach number, which you can get 1 equals 1 per 1.202, which we can like do the arc sin method, and we can get the Mach angle equals to 550.179 degrees, which we can divide right here. The size is 50.179 degrees. So we can conclude is a compressible flow, and it is a supersonic flow with the Mach angle of 50.179 degrees. On note, there is an analogy between compressible flow and open channel flow. The analogy of the compressible flow with open channel flow is the propagation of weak pressure impulses or sound wave in compressible flow can be considered to be comparable to the movement of small amplitude waves on the surface of an open channel flow. In each case, two-dimensional flow and open channel flow, the influence of the velocity of wave on wave pattern is similar. When the flow velocity is less than the wave speed, wave wave fronts can move upstream of the wave source and the flow is sonic, which is compressible flow we're talking, or critical, which is open channel flow we're talking. When the flow velocity is greater than the wave speed, the flow is supersonic, which is the compressible flow part, or is supercritical, which is the open channel flow part. In compressible flows, it has a meaningful dimensional variable which is Mach number, which Ma equals to V per C. Meanwhile, in open channel flows, an important dimensionless number is Froude number, which is Fr equals to VOC divided by in the root of G times Y. So we can define this as, since the speed of small wave on the surface of open channel flow is C, we can define it as COC equals to root GY, which we can substitute here equal for Froude number equals to VOC divided by COC, which if we take a look is very similar to MA equals to V per C, which how they're defining the dimensions is typically almost the same, but in a type of where the application is being held. So this is for open channel flow, and this is for compressible flow. I think that's all from me for the presentation today. Thank you very much for watching this. I am very sorry if there's like a minus in my presentation and stuff like that. Okay, I think that's all. Thank you very much. I'll be leaving now. Wassalamualaikum warahmatullahi wabarakatuh.